And Mr. Muhammad Al Khafaji, do you have my voice? Alaykum assalam. Okay. In the name of God, in the previous session we see some example for Banach algebras, and the last example is this A of the bar, the set of all analytic functions on this open unit disk. And we have some more example. And you can write this example. Let I express this example too. Let U, E and F be linear spaces. Then we denoted L of E and F, the collection of all linear maps from E to F. It is itself a linear space for the standard operation. It's very trivial that if, for example, T1 and T2 are two linear maps, then T1 plus T2 is a linear map 2, okay? So we have this example. Okay, example. Let E and F be linear spaces and L of E and F equal to the set of all T from E to F such that T is linear. T is a linear map. Then L of E and F by the following operation is a linear space. For all T and S, for example, in this space, L of E and F, we define T plus S of any x equal to T of x plus S of x for any x in E. Please note that T of x is an element of F, because we know that T and S are functions from E to F, okay? So that T of x and S of x are element in F, so that this is an element in F, so that S or T plus S is a function from E to F again. And for any T in L of E and F, and for any alpha in a scalar field, for example complex number, alpha T of x equal to alpha T of x, and again, so that alpha T again is a function from E to F. So that we have these two operations, T plus S and alpha T. It is very trivial that T plus S and alpha T are linear maps again. Okay? Trivially, T plus S and alpha T are linear maps from E to F, so that we have this space with these two operation, okay, plus and scalar multiplication. This is a linear space. Now let E and F be Banach spaces, so that we have norm in E and F. It is a subset of, okay, Banach. Then B of E and F, consider the family of all bounded linear operators from E to F. So if we consider this E and F be Banach spaces. Okay. At the first, E and F consider linear spaces, and in this case these two are Banach spaces. We know that a linear map a function such as f from E to F. Let me consider linear map at first. A linear map from linear map T from E to F is called bounded whenever there exists a real number m such that for any x in E, the norm of Gx is less than or equal m multiplied by the norm of x. Please note that the norm of Tx must be considered in F, but this x is an element in E, so that this norm consider the norm in E. The set of all bounded linear maps from E to F denoted by B of E and F, so that B of E and F is a subset of L of E and F. In this space B and E and F is a subspace of L of E and F, and it is very trivial. The operator norm on this space defined by the norm of T equal to the supremum of this norms such that X belongs to E and the norm of X is less than or equal 1. And also this is equal to the supremum of this node such that X belongs to E and the norm of X equal to 1. And also it is equal to the infimum of all M such that for any X in E we have this relation. Okay. And the proof of these two equalities is easy, and you can see this in many books. It is trivial that this is a node on B of E and F, okay? As an exercise, please let me write this for you. يرجي إثبات هذا المساواة كتدريب. Okay, do you understand, dear students? Do you understand? Okay. Prove this equality as exercises. But if you consider which of these equalities, and also we can write this as this supremum again. Okay, all of these are equal. This is a norm. This is a known function on B of E and F, and it is called the operator norm. Operator norm. And the proof of this is very easy, that this is a known because the norm of T is non-negative, for any T in B of E and F, the norm of T is non-negative, and also if T equal to 0, then it is trivial that this norm equal to 0, because if T equal to 0, all of this must be equal to 0, and so this supremum must be equal to 0. It's very trivial. Conversely, if the norm of T equal to 0, you consider in E this must be 0. So that for any non-zero element in E, this must be 0. I use this equality for example because if this equality is 0, this supremum must be 0. And all of these are non-negative, so that all of this must be equal to 0. All of this must be equal to 0, so that this must be equal to 0, and we conclude that for any x non-zero in E, this must be equal to 0. And finally, for any x in E, Tx must be equal to 0, because we know that T of 0 equal to 0. And for all non-zero, this must be equal to 0. So that for any x, T of x equal to 0, and so T must be equal to 0. So that we have this property that T equal to 0 if and only if then the operator norm of T equal to 0, and we prove this property in norm spaces. Okay, and also for any T in B of E and F, and for any alpha in complex number, we see that the operator norm of alpha T equal to the supremum of alpha T of x, such that x belonging to E and the norm of x is less than or equal 1, and this is equal to absolute value of alpha multiplied by the supremum of T of x, the norm of this in F, x belonging to E, and this norm is less than norm is E. Okay, less than or equal 1. All of this norm must be considered in E. Okay, it is trivial because x is an element in E. Okay, and this is equal to this absolute value multiplied by the norm of T. And finally, for any E and F, we see that the norm of this is operator norm, okay, T plus S equal to the supremum T plus S of X such that X belongs to E and the norm of X is less than or equal 1. And this is less than or equal this supremum T of X plus S of X such that X belongs to E and this norm is less than or equal 1 because this is less than or equal this and this is less than or equal these two supremum of Tx such that X belongs to E and this norm be less than or equal 1 plus the supremum of this set S of X, okay, the norm of S of X such that X belongs to E and this norm is less than or equal 1 and the first one is the norm, the operator norm of T and the second is the operator norm of S, okay, so that we have this property, the norm of T plus S is less than or equal the norm of T plus the norm of S. And in this case we see that the norm of alpha T is less than or equal the absolute value of alpha multiplied by the norm of T. So that this is a norm space so B of E and F with the operator norm is a norm space. Okay, and this norm space is a Banach space. Also B of E and F with the operator known is a Banach space. More generally, we have this proposition. If E and F are norm spaces and this is the operator norm on B of E and F, then B of E and F with this operator known is Banach or complete if and only if F with this norm is a Banach space. Okay? Or we can come right complete or Banach. Okay? Complete or Banach. Banach space or complete. Okay? Complete. In this case, because we consider these two as Banach spaces, so B of E and F is a Banach spaces. Okay? But we have this proposition. Please prove this proposition again as exercise. Okay? Please prove this. This is very nice. This is complete if and only if F is complete. So we have a Banach space. Now if E and F are equal, No, if E equal to F, we denoted so we have these spaces are Banach spaces 2. So L of E is an node space or is a linear space, and B of E is a Banach space. Because we consider E as a Banach space, okay? So that B of E, and E is a Banach space, okay? Now, in the next step, if we consider composition operation on B of E, then we see that for every S and T, for example, in B of E, TOS or SOT are in B of E. It is very trivial that SOT is linear. SOT is linear. SOT of x1 plus x2 equal to S of T of x1 plus x2, and this is equal to S of T of x1 plus T of x2 because T is linear, and this is equal to S of T of x1 plus S of T1 x2, and this is equal to SOT of x1 plus SOT of x2. And similarly, S O T of alpha x equal to S of T of alpha x, and this is equal to S of alpha T of x, because T is linear, and this is equal to alpha S of x. So that this holds for any x1 and x2 in E and alpha a scalar number, complex number, okay? x1 and x2 are element in E, and alpha is a complex number. Also, we see that SOT is bounded. Please note that trivially for any, since T is an element in B of E, or E and F, for any x in E, we have this inequality. This norm is F and this norm in E. Okay? This is very trivial because this is the operator norm, okay? The operator norm. Because we know that for any x, non-zero in x, this is less than or equal operator norm, because the operator norm is the supremum of these real numbers. So that for any non-zero element in X, in E, because we consider a function from E to F, okay? In E, we have this inequality. And so that we have this for any x. We have this for any x. In E, we have this property. Okay? Because this holds for 0, and by this holds for any non-zero element. So that is hold for any element in E. Okay? So if S and T are in B of E, we see that then for any X in E, S this node, okay, SOT of X equal to S of T of X, and this is less than or equal the norm of S multiplied by the norm of T of X, because S is bounded, okay, S is bounded. S is bounded. And also this is less than or equal this multiplied by this, the operator norm of S multiplied by the operator norm of T multiplied by the operator norm of X, because T is bounded. T is bounded. Okay? So we have this property SOT of X equal to or less than or equal, let me write this for you again, for any X in E, this node SOT of X is less than or equal the norm of S, the norm of T, the norm of X. This is a real number, and so SOT is bounded. This is our M, for example, okay? Consequently, if S and T belong to B of E, then SOT is an element of B of E. And also by this star we see that the norm of SOT is less than or equal the norm of S multiplied by the norm of T, because we know that the norm of SOT is the infimum of these m's. Okay, the infimum of these m's. There is no tab to these important inequalities. Okay, these equalities equal to the operator norm. We consider this, for example. Okay, okay, so we have this property that this is SOT. For simplicity, in the book we don't write composite operation. Okay, this is SOT. So that this norm is algebra norm. Okay, so the operator norm, is an algebra norm on B of E, and this is very important. And finally, the identity map is the unit in this Banach algebra, and identity map I, for example, from E to E by this function rule, I of x equal to x. Okay, is the unit of B of E. So B of E and the operator norm is a unital Banach algebra. Okay, and we have this important example. Okay, B of E with operator norm is a unital Banach algebra. Okay, dear students, do you have any questions? And goodbye for now. Goodbye.